Hi, I'm Deirdre Connolly. I'm with the Zcash Foundation. I'm presenting today with Conrado, who's also from the foundation. We're talking about Frost engineering updates. If you went to Chelsea and Liz's talk about an hour ago, this is building off of that. We're going to talk about how we're specifying Frost as a signature scheme specification, how many implementations of Frost that we have done in its various iterations, and why that led to the development of Frost Core, a library that we hope other people will be able to use to build Frost implementations for themselves, including several Ciphersuites that we've implemented for this, and our progress on creating a re-randomizable variant of Frost explicitly for use in Zcash, but anywhere else that wants unlinkable Frost threshold signatures. So as a recap, Frost is a two-round, the variant of Frost that we are talking about today is the two-round variant. This is the variant that is being specified as part of an IETF draft. Previous iterations have Frost had one round with pre-processing. This is 2 rounds, no pre-processing. So the way that you do Frost is you have some sort of keygen before you start this 2-round protocol. This can be via distributed key generation or using a trusted dealer to create and generate keys for you, but that's not specified in this draft. Once you have keys, a coordinator will send out an update to all possible signers, and the signing participants in this protocol will create nonces and keep them secret, and generate commitments to those nonces and send them out to the coordinator and their other parties. In the second round, the coordinator will send out the message to be signed and have all of the signing participants sign over that message and use the commitments that they saw in the first round as inputs to the signing share that they create, send those signing shares back to the coordinator. The coordinator aggregates those together and produces your threshold signature. One thing that we really like about this threshold signature for an application like Zcash is that the signature that you create is the same kind of signature as a signature created by a single party. It is a Schnorr signature. They are verified the same way, and you cannot tell that one is a threshold signature and another one is a single party signature, and you cannot tell which signing participants actually created that threshold signature when it's created. So this is very nice if you need to put your signatures on a public blockchain. If you went to Chelsea's talk and Liz's talk, Frost has been underway and going through lots of iterations and research for over 2 years now. So one of the first implementations was Chelsea's. She wrote some Rust to make that. We worked together to turn that Rust into an implementation for the sapling Zcash curve, jub, based on the variant of Frost that was in the original paper, aka 1 round with pre-processing, not the thing that we're specifying in our document. And then we also ported that for Palace, the curve that's used in Orchard, the NU5 update of Zcash. And then we started working on this IETF specification. So that means taking a bunch of code that was based on 1 round with pre-processing and turning it into 2 rounds, strictly 2 rounds, based on the IETF spec, and we would continue to update that spec, those implementations, as the spec continued to go through multiple iterations and improvements and clarifications, and we are about to cut version 8 of that spec, and that's 8 versions in about 8 months of work. So rapidly changing environment that we're trying to implement code for. And then we've implemented at least 2 Ciphersuites in the past, updated a new one, that's Ristretto, that's in the IETF document, and there are at least 3 others, and I think we've just added a 4, that we are interested in implementing as well. So a lot of code, a lot of churn in a lot of areas. Too many implementations are very hard to maintain. If you're trying to keep 2 of them in agreement, you may have lots of duplicated code. When you have multiple elliptic curves, there are things slightly different between doing stuff over one elliptic curve and doing them over another. This is hard to maintain. Errors come in. Anyone who implements cryptography can attest to this, and especially anyone who has to do some sort of protocol coherence between multiple implementations that in theory would agree with each other about what they're trying to do. So this motivated us, since we were writing a lot of this in Rust anyway, to try to make a generic implementation. And I'll show you some code in a minute about what that means, and if you're not familiar. This motivated the creation of the Frost core trait. So Frost core is a fully generic implementation of the Frost IETF specification, the 2-round variant. The only trait requirements that we expose as part of our package are things that come from the Rust standard library or the non-alloc standard. We do not require implementers who build on Frost core to pull in things like rand or anything that's not already available to you as a general Rust user, other external crates or types, and that was by design. And the big win that this gives you is that you can take a couple of crates for your favorite elliptic curve and your favorite hash function that goes with that and depend on Frost core, and you have a new fully compliant implementation of Frost, the specification, in about 300 lines, as opposed to thousands of lines, which we have done several times. So this is a big win. So the way you do this, you import Frost core, you implement these traits, and there's about 3 of them for an elliptic curve, for a hash function, and the high-level Ciphersuite that kind of wraps them all together. We expose generic tests and generic batch math for testing your concrete implementation when you have done it. So you can pull that in from your top level when you're like, oh, I want to run the full Frost protocol, but I want to execute it against my concrete instantiation using my favorite elliptic curve and my favorite hash function. We basically expose that for you. We've written those tests for you, and then you just kind of call that method with your concrete instantiation, and you get to execute over your full implementation. And then similar for batch verification math, which is kind of fresh and new. And then this is me replacing our implementation, our full implementation top to bottom of Frost on the Ristretto prime order group with an implementation that is just Ristretto using Frost core. I was able to remove almost 3,000 lines of code. And if you're an engineer, you know how good that feels. So here are the traits. This is the top level Ciphersuite trait. These traits are very close to kind of the API that we expose in the IETF spec. So top level, you specify a group. You specify the size, the shape of your hash output. You specify what kind of signature serialization looks like. These are traits that are just trying to target, like when you serialize these types, when you have an output, when you have a final signature and you're serializing it, what do they serialize into? And then we have these, it's 4, but in the new version, it's going to be 5 hash functions that give you different hash outputs. These are all domain-separated functions that serve specific purposes within the Frost protocol. Some of them give you bytes, and some of them, as you can see, give you scalars. And those are scalars as appropriately parsed under whatever scalar field that we will implement as part of your group. So this is depended on by the Ciphersuite association. This is a associated type for your Ciphersuite. So your group also defines its associated type, its field, what kind of type is the element of this group. And as you can see, it only needs to have adds and copies and clones and equals and moles. And I think that's it. These are not things that we require your group elements to implement from, I don't know, a group trait or a field trait or any other thing. We want it to be, we kind of wrapped all of this up into these traits so that you can directly depend on Frost core and in theory use whatever curve library or hash library that you want and not have to pull in a bunch of other things from the Rust ecosystem. That was kind of our goal. And then you also have to define these associated functions for giving the cofactor, giving the identity element, giving the generator element of the group, and then how you serialize and deserialize these elements. If you are operating on a prime order group, your cofactor is 1, the scalar value of 1. But we have a goal of interoperating with non-prime order elliptic curves. So we'll get to that in a minute. And then this is the rest of the field trait. It's kind of similar. You have a field with an associated scalar field element type, and then the serialization of such a field element. And then you have to give how you get 0, how you get 1, how you invert over the scalar field, how you generate a random scalar. I'm sorry, we have RNG core and crypto core as a dependency. A random non-zero scalar, and then again serialize and deserialize. And that's the meat of it, I would say. Using this, we have implemented Ristretto 255, as I said, and freshly P256. Conrado was our first guinea pig of doing this fresh. He did, I think, a very good job. I think he was able to come in fresh to Frost as a project and come up with this implementation based on Frost core in about a week. And it's good. So yeah, I would consider that the first success story for Frost core. I mentioned there's other Ciphersuites. We just merged in SEC P256K1 as a Schnorr signature, not an ECDSA signature where it's commonly used in Bitcoin because all of Frost is Schnorr, to the specification. So a thing that was sort of a nice to have is becoming more of a need to do very soon. And now our cofactor curves, ED 25519 and ED 448. This is why we have required and took out and added again the requirement to define your cofactor, because we want to make sure that if you are targeting a prime order subgroup on these curves, which is required for Frost, that we multiply out your cofactor, especially for our batch verification and anywhere else where we have to make sure that we are operating in the prime order subgroup of these curves. I think cofactor curves are an evil and we should get rid of them. As Chelsea and Liz mentioned, lots of work has been happening in Frost and thus reflected in the IETF spec over the last 6 months, basically. So this is the optimization in Frost 2 that was mentioned earlier. We had first gone with Frost 1, where every signer had to do an extra scalar multiplication. And then we had tried to do this optimization where there is a single scalar optimization for all possible signers or numbers of signers. But as mentioned, that introduced a signer set malleability issue, not a signature malleability issue, just whether you can prove or be certain that the number of signers that started the protocol in round 1 are the ones that finished the protocol in round 2. And based on everything else that we were doing in the spec, we just decided we'll back it out. We'll go back to Frost 1 where we don't have this issue, and that's where we're going with now. Oh, I did the wrong thing. And one other thing that we added is that we were trying to specify our verification formula for you have a threshold signature, it should be the same as a singleton signature. How do you verify it? We had these subroutines in our specification, and we were trying to make them work for prime order groups, cofactor curves, yada, yada, yada. And it wasn't working because of IETF spec reasons, and I'm going to put a lot of blame on the ED 25519 specification for this. So the way that we kind of split the difference is we have verification defined per Ciphersuite. This allows us to point all of our prime order groups to a verification that is explicitly about prime order groups in our spec, but we also can point to, if you're trying to verify something that's compliant with ED 25519, we have to be compliant with the verification equation in that document for RFC 8032. And this seems to be fine. They should fix RFC 8032. And now I hand it off to Conrado.
Thank you. Oh, thanks. Yeah. So Frost is super cool, but this is Ecom, so we're especially interested in how to use Frost with Zcash. And the main reason for that is with Frost, we can enable a lot of applications like sharing custody of your wallet, stuff like that. In order to explain how we do that, how we use Frost with Zcash, you need to understand a little bit about how Zcash uses signatures. So Zcash is a complex protocol, but the main part that is required to actually authorize a transaction is to generate these spend authorization signatures, which are digital signatures. This is for sapling in Orchard protocols. Sprout was a bit different. But basically what happens is that when you create a transaction, when you want to send the cash to someone, Zac to someone, you need to digitally sign the transaction with a private key. So this is a spend authorization key, is in the specs called ASK, and is derived from your wallet seed or main secret. So the thing is, these are not plain digital signatures. They rely on a property called re-randomization, and this is needed in Zcash due to the privacy properties of Zcash. So if you were to just simply sign a transaction, you will need to publish a public key. So if you do that for 2 transactions, the same public key would be published, and anyone could tell that those 2 transactions came from the same person. So Zcash employs this re-randomization, which basically every time you sign a transaction, you compute a randomizer, which kind of scrambles our private key. It turns into a new private key, and with that, with a new public key, a randomized public key. And of course, this, when you generate a transaction, you generate the zero knowledge proof, and the zero knowledge proof proves that the randomized key is linked to the original key, but in a zero knowledge fashion. So no one is able to check if 2 public keys are from the same person, but you can verify that transaction, that the transaction makes sense. So we need to do that with Frost, right? So we had to do some adaptations to Frost to work with Zcash, to add re-randomization to Frost. One main property is that Frost just relies on authenticate channels. Of course, you can use a confidential channel, but it only relies on authenticate channels. But for re-randomizer Frost, you need a confidential channel, and of course, if you publish the transaction or the randomizer in clear text, the attacker can link the transaction. So this is a bit different from regular Frost. So like I mentioned, when you sign a transaction, generate a randomizer. So in Frost, you have this role of the coordinator. You can build Frost without a coordinator or with a coordinator, but for re-randomized Frost, we are assuming there's a coordinator, and that makes sense because when you create someone is creating the transaction, someone is publishing the transaction, so there's usually this party that has this coordinator role. So the coordinator chooses the randomizer and sends to all participants. The participants, when they're computing their share of the signature, they incorporate the randomizer into the computation. And after all participants compute their shares, they send back to the coordinator, and the coordinator also adds the randomization to the final signature. So that works, right? With some small adjustments, we can make Frost work in a re-randomized fashion, so it can be used with Zcash. So this randomized public key is published along the transaction. So, and like I mentioned, the zero knowledge proof allows you to check if that verifying key is actually the key that's authorized to generate that transaction. So here's the main scheme of Frost. So what changes is that in round 2, right, the round 1 is related to commitments. That doesn't change for re-randomized Frost. But the beginning round 2, the coordinator generates the randomizer, alpha. It's a random scalar value. It sends to all signers in a confidential channel. And the signers use alpha in the computation, and also at the end, the coordinator also uses alpha to add a term to the signature, and that computes the final signature. So this work is happening. Our final goal here is to publish a zip, right? A Zcash improvement proposal, which is going to specify how to use Frost with Zcash. So we have the zip kind of ready. We're just doing some final reviewing. Chelsea is going to write also a proof of security, but the zip, we're going to submit the zip officially soon. So if you're interested in that, just check the zips repository. We'll create a PR there soon. We have a working code, a proof of concept code that works. We have already tested, but we need to clean up a bit, just branches in random repositories. So our next step is to also clean up that code and make it available as a crate. And also related to Frost in general, if you're interested, there's the main Frost repository. The version 8 that Deirdre mentioned of the specification is coming soon. You can also check on that other repository. And after we complete these goals, we're planning to work on distributed key generation that I think was already mentioned, and also supporting other curves. That's it. Can go for some questions.
Check. Okay. So we have a couple questions. The first question is, what is the concrete performance characteristics of your Ristretto Frost implementation?
Very good. I can run more concrete benchmarks and update you async, either on the ZF Discord, or maybe in the ZCon3 Discord. But they're quite good. Ristretto is based on under the hood Ed 25519, and we've done a lot. There's a lot of inherited math between all of these Edwards-based curves, and so Frost on Ristretto is comparatively performant as Frost on Ed 25519 and JubJub, which we also have done.
So there's a follow-up question which doesn't quite parse to me, but I'm going to read it and we can answer it however we want. So the follow-up question is, would it be feasible to run a multi-signature with 2-3 threshold and around 100 participants?
Can you repeat the second part?
Would it be feasible to run a multi-signature with 2 out of 3 threshold and 100 participants?
So 2/3 of 100 possible. Well,
okay. So there we go. So 2/3 of 100 participants.
It's very possible. We can benchmark that to see how slow it is, but it's absolutely possible. Yeah.
Okay, I think it's asking about like how does the performance scale with more participants?
We've done some benchmarking up to 64 parties, but we can just run those up to 100, like either 100 signers or where the threshold is 100, or the threshold is 2/3 of 100 or whatever.
Yeah.
So what is 2/3 of 64?
I have to go look it up. I don't have it off the top of my head.
Cool. The next question is, why is scalar an associated type of field rather than group?
Because it is basically how we are representing the scalar field, not the field of, basically because we are dealing with the group and the addition of elements over the group, which is described as scalar multiplication. The field is not the field that the group, aka the curve, is defined over. So these are not equals things. It's the scalar field.
2 more questions.
Yeah.
Okay, is Frost core no standard compatible?
No, right now it is quite reliant on standard, but I think we want to explore how we can make it no standard compatible.
Yeah, it should be possible.
Yes. I don't think, right now we have not done that and ascertained it. We think it's very doable.
Okay, follow-up question, who would act as the coordinator for the Zcash chain?
Oh, the wallet, basically. We think that whoever is, we've had these discussions with Dara and other cryptographers at the Electric Coin Company. In the Zcash case, the key thing that the coordinator is privileged to is the randomizer, and they have access. If you have access to the randomizer, you know how to link these 2 signatures. So if you also know the witness in however you're creating your zero knowledge proof, even no commitment tree and anything else that you're witnessing, whoever is doing that should also be the coordinator when you're creating this threshold signature. And generally that party is the wallet, whoever is initiating this signature.
Also, something interesting to note is that we trust the coordinator with the privacy of the transaction.
Yeah.
But the coordinator, even if you consider some scenario where the coordinator is malicious, he won't be able to generate, authorize a transaction or discover the signature, the key share of a participant.
Yes, that's correct.
Excellent question. Does Frost take any specific steps to be quantum safe?
All the security reductions of Frost rely on Diffie-Hellman or one-word Diffie-Hellman. We do not know right now how to do something like Frost in a post-quantum setting with quantum resilient security reductions. So, sorry.
Future work.
Yes, future work. We got this question when I presented Frost stuff at IETF. Same idea, like, how could we do this with a hybrid mode? And in theory, if there was a fully quantum resistant threshold scheme that also worked well in 2 rounds, and had the same security and privacy properties, maybe you could just slap them together and do hybrid, optimized threshold. But it's a complete shrug right now. That is not available to us right now. That's a lot of good research work to do.
Okay, we have 2 minutes left, so I guess
good questions.
These are great questions. I have a question,
yeah.
Which is, what are some of the things you're looking forward to working on the most in some of this? So some of the things you wish you could have done so far, or the things you're kind of looking forward to implementing or cleaning up?
We just merged the fully generic batch stuff. So in theory, if you build your implementation on Frost Core, you get a for free, very fast batch verification of your Schnorr signatures. And you kind of get that even if you don't do the threshold part. You could just do singleton signatures and you implement these types and you get fast batch verification for free. That just got merged in, but should be available. And some of the other things that we're kind of looking on is, I won't put that in public, but we're trying to tidy up all of this code and publish it and make it very readily available. And I am very much looking forward to the spec getting done and accepted by the CFRG.